Hello everyone. In this lecture we are going to learn about Tubesheet Design with respect to UHX for U-tube type configuration. Part 3. Hope you have already watched Part 1 and Part 2. Our flagship courses are Master Static Equipment Design and PVE Light, ASME Section 8 Division 2, and Master Welded Storage Tank, as per API 650. We have curated courses to suit your learning needs. So do visit our learning platform for more details on scutoid.thinkific.com.
Now, let us try to understand the calculation. So what we have taken the common sandwich type D type configuration. Okay, and by using that, let us calculate the thickness. See the procedure. So step 1, determine all the effective dimensions. That is my first step, which we just did. We calculated all the effective dimensions. Now step 2, we are trying to calculate the ratio of rho S and rho C. What is rho S? Rho S is nothing but GS divided by GS means where your in the shell side where your bolt are actually acting the loads, which is actually the mean dia of the gasket. Okay, where actually that due to bolts, yes, gasket load reaction. So where because of bolts, the gasket reactions will be acting on the tube sheet, and that is the GS. Okay, so because basic for your tube sheet, the load apart from pressure, load will be because of bolts also. Okay, and in this case, in the sandwiched case, it is getting transferred through the gasket. Okay, so it is ratio of GS divided by DO. Okay, DO is what? Outside tube limit, OTL. Okay, so basically it's unperforated area what we are trying to calculate. The ratio of unperforated area in right hand side. Okay, if you try to analyze this equation, what we are trying to do is to find out this area. Okay, so this is actually the unperforated area. So rho S, shell side unperforated area, means basically the dimensions. But if we see from the side, basically it will become area. So here it is only the dimension. So unitless dimension, we can say. Okay, great. Rho S and rho C. Rho C for channel side. So same parameters GC, which is the again gasket reaction for channel side divided by D naught. Okay. In most of the cases, it will be same. Okay, because GS and GC, typically your reaction will be at some same location. But if your ID is different in some cases, okay, that also may be possible, then this rho S and rho C will become different from each other. Otherwise, it will be same, because most of the time you'll see GS and GC are same, and D naught is anyway same for all the cases. Okay, so that will give you now the we have found the dimensions. Okay, the ratio. Now we'll be using that ratio because that ratio is related to what? Unperforated dimension, you can say. Okay, so the linear dimension of unperforated area. Now because of that, what is the moment getting created on that area? That we'll see. That is the calculation of MTS. Okay, so MTS is basically the moment coming on that portion because of the loads. So now here the load is not because of gasket. So we'll also be calculating because of that, the gasket reaction load coming because of bolt load. This is not the load. This is because of, see, this area, if it is different, okay, this linear dimension, and there is pressure, internal pressure. Because of internal pressure, there will be moment created, okay, on this unperforated portion. That is what we are trying to calculate. Okay, so that is the MTS. This is the formula for MTS. If you see, basically rho s, the shell side ratio, and the channel side. That is the difference of that. If the pressure is same in both the side, and also this ratio is same, the reaction is coming exactly like what we have shown, like same point, then this MTS will not be there. It will not exist. Okay, and that we can relate, right? If there is, the pressure is same, and if this linear dimension is a little bit different, then slight moment will be there. But if pressure is also same, the point of acting of the bolt load, that gasket reaction is same, then this final, the area which is left is same. So equal, both side equal moment. So basically no moment. So MTS will become 0. Okay. Okay. In the case where equal pressure. Okay. Now, step 2, we have calculated what we calculated in step 2. We calculated the turning moment MT for that unperforated portion because of pressure. Now, some more ratio, E star E and nu star. Okay, that is the nu star. So there will be some, don't put lots of thought in this ratio calculation. It will not give much meaning. Okay, so we find some ratio. You can say, like that. There are figures to use. Okay, so first H by P. H is nothing but the tube sheet thickness. Okay, we have already assumed tube sheet thickness because, like I said, we are trying to find the stress or the thickness. So tube sheet thickness is already there with us, divided by pitch, that is H by P. Mu star, we have already calculated. Now, based on mu star, we can calculate E star divided by E. E is the modulus of elasticity. So new modulus of elasticity. E star is what? It's also effective modulus of elasticity. Okay, it is a combination of tube plus tube sheet material. Okay, getting it? Because finally this material is nothing but mix of that. So E star, that E star we find by using this figure. Okay, there is a figure given in code, and by using mu star and H by P ratio, we can get this E star calculated. Okay, and similarly, nu star is again by similar figure, and you can see that this changes for the pattern. Tube pattern also plays important role. Okay, and it's pretty obvious, right? Because finally we are trying to relate the material with tube. So how they are positioned, that will play a role. So there is figure, by that we'll be able to get a nu star also. But why we are doing all that? Okay, there is some A by D ratio. A is nothing but the overall outside diameter of the tube sheet, that is A, divided by D naught. You already know OTL. So A by D naught first we'll calculate. Then there is something called coefficient F. Nu star we have calculated. E star we can calculate by using E star by E ratio, which we calculate. Okay, so all these values are there. We got something, nothing to put any thought here. Okay, now, so by using all that, first what we calculated, the first step was to calculate the differential moment, which is actually creating a turning moment because of pressure in the unperforated region. That time we said that because of bolt also, because if they are not equally placed, differential, then they will not counter. They'll be again adding some stress, adding some moment to that unperforated area, right? Like this is the section. Okay, and if I have a load which is going in the same direction, then because bolt load will counter each other, okay? So no moment. Okay, but if it is differential, like you see in the right hand figure here, if there is a differential gasket reaction, then there will be moment, because of bolt load. Couple, so it will exert additional moment on the unperforated. So we'll get that moment. Okay. And if I add that to the earlier one calculated, that will be my moment, which is total moment on the unperforated tube sheet. Okay. Great. So I have calculated unperforated moment, moment on the unperforated tube sheet. Now, my point of concern is not the unperforated part. Okay, because there is full material. For me, the weakest link is where the perforation starts, isn't it? Because the less material is more critical. So finally, because of that moment which I have calculated on the unperforated region, that will exert the maximum moment at this location, at the periphery. Okay, so this is the formula to convert that m star which we have calculated into a moment at periphery. So that is one moment acting at this point. Now center also, there will be moments because of that. Okay, so center also I'll calculate. Okay, so there will be periphery moment, which is because of the unperforated region, whatever load which we saw, because of differential pressure, and also because of if it is forming a couple, the gasket reaction, if both are different, then there will be additional moment, and the pressure. So all combined at the center, there will be m nod moment, which can be given like by this formula. Okay, so we have moment at the periphery, okay, and moment at the center. Both places are critical for me. So I have the moment at both the location. Now we don't know which one will be maximum. So I'll calculate the maximum moment. So whatever is maximum among them, we'll calculate it. Now, few of you might be thinking that, see, MP, we are adding this term. So why not MO is more than MP always? Can I say that if MP, we are already adding this term, so this should become more MO. This moment at center should be more. Any thought on that? Are you thinking like that? That MP will be less because we are adding here. Yes. Now, the moment itself, like this PS minus PT, if PT is more, this will become negative. Okay. So we don't know what will happen. Here also, it can be plus minus. So we don't know what will happen. So better is to calculate and then take the max of these two moments, apply that, and calculate the bending stress. Why we are calculating moments? First of all, once the moment is coming into picture, you already know that there will be some bending stress which will be calculated, okay, by using that. So now this is the bending moment formula. If we can see, it looks very similar to m by z. Okay, so m is there divided by that ratio mu star h minus h dash g square, that you can consider as z. So m by z is my bending stress. So I have my bending stress calculated. So once I have the bending stress, and if the bending stress will not be compared with allowable. See, let us see, the tube sheet is of carbon steel. What is my allowable? 138. So will I compare that bending moment with allowable? No, it is 2s. No. Now what is the reason? If you know the different types of stresses, there the reason lies that I can permit more stress for bending type. Okay, so here there is bending stress. So bending stress will not directly result into the failure. Okay, because bending moment across the section, if you see, one side plus, other side minus, so overall it's nil. Okay, so that is the reason it does not result into failure. It may have the fiber elongation extended at the topmost part, So we allow more stress. Okay, we can, even the stresses are 2s, still it is acceptable. So we are comparing that bending stress which we calculated with 2s. Okay. Now if the stress which we calculated and we got it more than 2s, then we'll have to now again assume a higher thickness and redo this part, okay, completely. So that is what we'll have to do. So bending stress we have calculated. The second part which will be playing again a role, which is shear stress. Okay, the tube sheet will exert shear stress also, and the shear stress definitely will be very critical at this periphery, because there the tubes are there, and that is my weakest link. Okay, so perimeter length is very much required. So shear stress tau can be given like this. You already have a formula. So with tau, we'll be able to get the shear stress. Shear stress will be compared with 0.8 s. Okay, not even s, only 80% of allowable. Okay, or 0.533 times of yield. Whatever is the minimum, that will be your comparison for tau shear stress. Okay, so once I have tau and bending stress calculated, my thickness, if I got through all, the stresses are within limit, I'm good enough. My tube sheet is designed. Okay.
For in-depth training. And to learn more about these courses, register with the link in the description.